Hello everyone. Welcome to the next section of the course, Using Decision Trees to Make a Medical Diagnosis. In this section, we will learn all about decision trees and how to apply them to both classification and regression tasks. We will talk a bit about overfitting and ways to avoid this phenomenon by tweaking pre-pruning and post-pruning settings. Finally, we will apply decision trees to medical data in order to detect cancerous tissues, and we will combine multiple trees into what is known as a random forest. Now we move on to the first video of this section, that is, understanding and building decision trees. In this video, we will start by understanding decision trees. Then we will learn the procedure and make an attempt to build our first decision tree by implementing the concept of pre-processing data and constructing the tree. So let's look at what is decision trees. It is a simple yet powerful model for supervised learning problems. Like the name suggests, we can think of it as a tree in which information flows along different branches, starting at the trunk and going all the way to the individual leaves. This is basically a decision tree. As you can observe in this figure, a decision tree is made of a hierarchy of questions or tests about the data, also known as decision nodes, and their possible consequences. Let's say we have a dataset consisting of a single email, so we will consider this email as a data. In case you were wondering, I have nothing against Nigerian princes or their email habits, but their reputation became victim of a popular email scam in the early 2000s, which makes for a good pedagogic example. The previous email is a slightly shortened version of a common email scam listed on this link. By including these lines of code, we are vectorizing an email in much a similar way as we did the previous section using scikit-learn's count vectorizer. As applied in the previous section, we will have a look at the feature names in X using this function. For the sake of clarity, we focus on the first 5 words only, which are sorted alphabetically. Then we will execute this line of code to find the corresponding number of occurrences. This output tells us that 4 out of 5 words show up just once in the email, but the word account actually shows up twice. Like in the last chapter, we typed x.toArray function in order to convert the sparse array x into a human-readable array. The result is a 2D array, where rows correspond to the data samples and columns correspond to the feature names described in the previous command. Since there is only one sample in the dataset, we limit ourselves to row 0 of the array, that is, the first data sample, and the first 5 columns in the array, that is, the first 5 words. So, how do we check if the email is from a Nigerian prince? One way to do this is to look if the email contains both the words Nigerian and prince. For that, we will enter and execute this line of code. Then we will execute this line of code to verify if the email contains prince word. As you can see, it says false. What do we find to our surprise? The word prince does not occur in the email. Does this mean the message is legit? No, of course not. Instead of prince, the email went with the words head of state, effectively circumventing our all-too-simple spam detector. I think we are ready for a more complex example. As promised earlier, let's move this into the medical domain. Let's consider an example where a number of patients have suffered from the same illness, such as a rare form of basorexia. Let's further assume that the true causes of the disease remain unknown to this day, and that all the information that is available to us consists of a bunch of physiological measurements. For example, we might have access to some information such as a patient's blood pressure, cholesterol level, gender, age, blood sodium concentration, and potassium concentration. Based on all this information, let's suppose a doctor made recommendations to his patient to treat their disease using one of 4 possible drugs: drug A, B, C, or D. Execute this line of code to list the data available for 20 different patients. Here, the dataset is actually a list of dictionaries, where every dictionary constitutes a single data point that contains a patient's blood work, age, gender, as well as the drug that was prescribed. Now let's understand task by understanding the data. The inputs to our machine learning algorithm will be all blood values, age, and gender of a patient. Thus, the output will be a prediction of which drug to prescribe. Since the drug column is categorical in nature and not numerical, we know that we are facing a classification task. Thus, it would be a good idea to remove all drug entries from the dictionaries listed in the data variable and store them in a separate variable. For this, we will go through the list and extract the drug entry with this line of code. Since we also want to remove the drug entries in all the dictionaries, we will go through the list again and pop the drug key. We add a semicolon to suppress the output, since we don't want to see the whole dataset again. Now let's look at the data. We will focus on the numerical features first: age, K, and NA. These are relatively easy to plot using matplotlib's scatter function. So we will first import matplotlib as usual. Then we will plot the potassium level against the sodium level for every data point in the dataset. We will go through the list and extract these feature values by executing this line of code. We will do the same for the sodium and potassium levels. Then we will execute this code snippet to pass these lists to matplotlib's scatter function and generate the data plot. Post-execution, this plot is generated, which displays sodium and potassium levels. However, this plot is not very informative because all data points have the same colour. What we really want is for each data point to be coloured according to the drug that was prescribed. For this to work, we need to somehow convert the drug labels A to D into numerical values. A nice trick is to use the ASCII value of a character. If you have done a bit of web development before, you may already know that every character has a corresponding ASCII value, which you can find at this web link. In Python, this value is accessible via the function ord. For example, the character A has value 65, that is ord A equals 65, B has 66, C has 67, and D has 68. Hence, we can turn the characters A through D into integers between 0 and 3 by calling ord on them and subtracting 65 from each ASCII value. Let's implement it for every element in the dataset using this line of code. Then we will pass these integer values to matplotlib's scatter function, which will know to assign different colours for these different colour labels, as we are using C equals to target argument in this block of code. Let's also increase the size of the dots using this argument and label our axes so that we know what we are looking at. The preceding code will produce a figure with 4 subplots in a 2x2 grid, of which the first 3 subplots show different slices of the dataset, and every data point is coloured according to its target label, that is, the prescribed drug. What do these plots tell us, other than that the dataset is kind of messy? Can you spot any apparent relationship between feature values and target labels? There are some interesting observations we can make. For example, from the first and third subplot, we can see that the light blue points seem to be clustered around high sodium levels. Similarly, all red points seem to have both low sodium and low potassium levels. The rest is less clear, so let's see how a decision tree would solve the problem. Moving further with pre-processing the data. In order for our data to be understood by the decision tree algorithm, we need to convert all categorical features, that is, sex, BP, and cholesterol, into numerical features. The best way to do that is using scikit-learn's dict vectorizer. Like we did in the previous section, we will feed the dataset that we want to convert to the fit transform method. Here, data pre contains the preprocessed data. Next, we want to look at the first data point, that is, the first row of data pre. So we will match the feature names with the corresponding feature values by executing these 2 lines of code one by one. From the output, we can see that the 3 categorical variables, blood pressure, cholesterol level, and gender, have been encoded using one-hot coding. To make sure that our data variables are compatible with OpenCV, we will convert everything to floating point values using this block of code. Then all that's left to do is to split the data into training and test set. Remember that we always want to keep the training and test sets separate. Since we only have 20 data points to work with in this example, we should probably reserve more than 10% of the data for testing. A 15:5 split seems appropriate here, so we order the split function to yield exactly 5 test samples. In this video, we got an overview of decision tree. Then we demonstrated steps to create decision tree.